Have you ever wondered why every year on Earth seems to be getting hotter and hotter, and weather events are getting worse and worse? Does the Earth have a fever? Or maybe the moon broke up with the Earth, and now it's steaming with rage and creating all of this bad weather? Okay, obviously not. But this isn't too far off from some of the conspiracies other people come up with. Instead of taking wild guesses, we can figure out what's really going on with a better understanding of the climate. The Earth's atmosphere is broken up into 5 different layers. First, the troposphere, where humans and all animals exist, is the lowest atmospheric layer. As we go up through the troposphere, the temperature decreases and eventually we reach the stratosphere. The stratosphere is the second layer. It's where passenger planes can be found. Temperatures rise as we go higher in the stratosphere. Eventually, we reach the mesosphere, the thermosphere, and the exosphere, which are the outermost layers of the atmosphere. The thermosphere is important for absorbing and blocking lots of the high-intensity energy coming from the sun. But what actually is the atmosphere? Well, it's a collection of gas particles, or the air, that surrounds us and which we breathe. But understandably, it can be hard to visualize what the atmosphere is made up of, because we can't actually see gas molecules with our eyes. Right now, we're looking at the atmosphere on a microscopic scale. For comparison, this is a red blood cell, nearly 400 times wider than the collection of gas molecules. So, on such a tiny scale, it makes sense why we can't see all these air particles with our eyes. Let's now think about what gases make up the air we see here. The atmosphere is about 78% nitrogen gas, 21% oxygen gas, and about 0.9% argon. If you add these percentages up, these gases make up about 99.9% of the atmosphere. These are constant gases, meaning their abundance remains relatively constant over long periods of time. But what about the other 0.1%? The atmosphere is also made up of gases called variable gases, which change in their abundance over days to years. These gases include carbon dioxide, methane, nitrous oxide, fluoride gases, and water vapor. Water vapor is highly variable and can account for anywhere from 0 to 4% of the atmosphere in a given region. Carbon dioxide is the most important greenhouse gas simply because of its abundance with nearly 420 parts per million. To make sure we aren't confusing constant and variable gases with well-mixed gases, I'm going to use carbon dioxide as an example. Describing a gas as constant or variable refers to how long it stays in the atmosphere. Carbon dioxide, for example, persists in the atmosphere for hundreds to thousands of years. This may seem like a long time, but in the billions of geologic years the Earth has experienced, this is relatively short. We also see that the concentration of carbon dioxide fluctuates massively over 1,000 to 100,000 year periods, so we call this a variable gas. Looking just at the last 200 years, Earth has experienced just under a 150 parts per million change in carbon dioxide concentrations. Now, despite its relatively short lifetime, carbon dioxide is an extremely well-mixed gas. This means that it is very evenly distributed and will be found at nearly the same concentrations no matter where you are on the planet at a specific period of time. Before we go deeper into greenhouse gases, let's make sure we understand concentrations and parts. When we talk about percentages of gases in the atmosphere, we are dealing with concentrations. The concentration of a given gas in the atmosphere is determined by dividing the volume of the gas by the volume of the air that it is within. In other words, if you take a cube of air from the atmosphere, 1 cubic meter in volume, you can find the concentration of nitrogen by taking the volume that nitrogen takes up in that cube and dividing it by the total volume of the cube. Across the globe, we see that about 78% of the atmosphere is nitrogen. This means that if you take any random cubic meter of air from the atmosphere, about 78% of its volume should be made of nitrogen. But what if we want to describe much smaller concentrations, such as a gas that makes up 0.0001% of the volume of the atmosphere? In this case, we use parts per million, parts per billion, or parts per trillion. These simply make it easier to describe very small concentrations. 1 part per million means that if you take 1 million molecules of air from the atmosphere, one of those molecules will be the gas of interest. In the case of carbon dioxide, 426 parts per million means that for 1 million molecules of air, 426 molecules are carbon dioxide. This is much clearer than saying carbon dioxide makes up 0.042% of the volume of the atmosphere. Parts per billion and parts per trillion also follow these same rules. So, 1 part per billion means for 1 billion gas molecules, 1 molecule is the molecule of interest. Now, we're going to look at some of the main greenhouse gases in the atmosphere. We haven't yet developed a comprehensive understanding of what a greenhouse gas is or what it does, but for now, I want you to think of them as gases that trap heat in the atmosphere. In the next video, we'll learn about the physical processes that lead to the greenhouse effect. Carbon dioxide is the most important and well-known greenhouse gas. This gas is made of one carbon atom and two oxygen atoms in a linear atomic shape. As we know, the atmosphere consists of about 426 parts per million of carbon dioxide. At this point, you might be thinking that this sounds like an astoundingly low number, but let me put this into context for you. When you breathe in air from the atmosphere, you are inhaling nearly 25 sextillion molecules. This is an almost unfathomable number. In each breath of air, we are breathing thousands of quadrillions of carbon dioxide molecules. So as you can see, while 420 parts per million might seem low when we're talking about only a couple million particles, on a global scale where there are quintillions of CO2 molecules in just half a liter of air, this is still extremely significant. In the atmosphere, carbon dioxide is often considered the most important greenhouse gas because it's the most heavily emitted gas by humans. Often, we call emitted greenhouse gases like carbon dioxide anthropogenic emissions. In Latin, anthro means human, and genic means originating from. So, anthropogenic means that these atmospheric gases are emitted by humans. Humans emit carbon dioxide whenever we drive, produce energy, or farm crops, because we're burning fossil fuels. Because of this, nearly 40 billion tons of carbon dioxide are emitted into the atmosphere every year. This 40 billion number may seem arbitrary right now, but let's look at the emissions of some other greenhouse gases to compare. Methane is another potent anthropogenic greenhouse gas that is primarily generated through agricultural practices, wetlands, and fossil fuel burning. In farm and wetland settings, methane is primarily produced as organic matter is decomposed. Methane is a particularly interesting greenhouse gas because of its interactions with hydroxyl radicals in the atmosphere. When this happens, methane can be converted into carbon dioxide or water. As a result, methane emissions can also increase the abundance of other greenhouse gases. Methane lasts in the atmosphere for about 12 years and has a concentration of about 1,900 parts per billion, with about 300 million tons emitted per year, as compared to carbon dioxide's 40 billion tons emitted per year. Nitrous oxide is another anthropogenic greenhouse gas and is primarily emitted from agricultural activities. Nitrous oxides last in the atmosphere for about 110 years and exist at a concentration of about 337 parts per billion, with about 10 million tons emitted per year. Chlorofluorocarbons and hydrochlorofluorocarbons are both fluorinated greenhouse gases. Chlorofluorocarbon was previously used as a refrigerant, but has devastating effects on the ozone layer. Chlorofluorocarbons have since been phased out in many nations after the Montreal Protocol put restrictions on their use. Hydrochlorofluorocarbons were developed as a replacement for chlorofluorocarbons because they don't have the same effect on the ozone. However, they are still a potent greenhouse gas that can take years to thousands of years to leave the atmosphere. Hydrochlorofluorocarbons exist in a very low and variable concentration in the atmosphere. There are also other fluorinated gases in the atmosphere that exist in extremely low concentrations. But is there a difference between these gases in the atmosphere other than just their abundance? Yes. We often use the ranking system known as global warming potential to determine how strong a greenhouse gas is relative to carbon dioxide. So, the benchmark gas for this ranking is carbon dioxide, which is assigned a value of 1. This value has no transferable meaning for the strength of carbon dioxide. It's not 1 year of warming or 1 degree Celsius of warming. It's simply saying that some amount of carbon dioxide will cause some amount of warming. Methane has a global warming potential of 21. This means that a certain amount of methane has 21 times the warming effect as the same amount of carbon dioxide. In this ranking system, values are often determined over a 100-year period. So, for instance, 1 ton of methane has 21 times the warming effect as a 1 ton of carbon dioxide, meaning the warming from 1 ton of methane is equal to the warming from 21 tons of carbon dioxide. Nitrous oxide has a global warming potential of 310, so it has 310 times the warming effect as the same amount of carbon dioxide. It's important, when talking about global warming potential, that we are comparing the same amount of carbon dioxide and our gas, because otherwise things can get confusing. We're not saying that methane has 21 times the warming as carbon dioxide overall. We're simply saying that some amount of methane has 21 times the warming effect as the same amount of carbon dioxide. This is why carbon dioxide is still the most important greenhouse gas. Although it's not the most potent greenhouse gas, it's the most abundant, and so it massively overpowers the others. But this doesn't mean the other gases aren't important. If we take the 10 million tons of nitrous oxide emitted and multiply it by the global warming potential of nitrous oxide, we see that these 10 million tons are equivalent to over 3 billion tons of carbon dioxide being released. While this is less than the 40 billion tons of actual carbon dioxide being released every year, this is still very significant. At this point, we've left out some other greenhouse gases and will now go over them. Ozone is a type of greenhouse gas that protects us from the UV radiation in the stratosphere, but it can cause warming when it's in the troposphere. Ozone has a concentration in the troposphere of a few parts per billion, and is not often given heavy focus as a greenhouse gas because it only lasts for a few hours to a few days in the troposphere. We more often focus on stratospheric ozone, which will be reviewed in later lessons. Water vapor is the most abundant greenhouse gas, making up about 4% of the atmosphere in some areas. Although we wouldn't describe this large of a concentration in parts per million, for reference, this is about 40,000 parts per million. But why don't we consider it the most important if it's the most abundant? Well, aside from its extremely low global warming potential, which makes its abundance more negligible compared to other gases, we often don't focus much on water vapor because concentrations of water vapor in the atmosphere are not directly changed by human activity. In other words, humans don't directly emit water vapor into the atmosphere in large amounts. It's mostly not anthropogenically emitted. Rather, water vapor concentrations are indirectly altered by human activity through a water vapor feedback loop. This feedback loop first starts with other greenhouse gases that are emitted by humans, such as carbon dioxide, methane, and nitrous oxide. As we know, on a basic level, greenhouse gases trap heat in the atmosphere and cause it to warm up. This warming causes water on the Earth's surface to heat up and evaporate into water vapor at quicker rates. This happens because hotter temperatures allow molecules of air to move faster, creating more space for water vapor. This water vapor, which is a greenhouse gas, then heats up the atmosphere more, causing more water to turn into water vapor. And then this cycle continues, generating more warming across the globe over time. While water vapor is clearly an important greenhouse gas, we can see why we focus on anthropogenic emissions over water vapor. Because anthropogenic emissions drive increases in water vapor and cause this feedback to strengthen. So, this all means that decreasing anthropogenic emissions is the key to weakening the water vapor feedback loop. In the next videos, we'll be continuing to learn about the greenhouse gas effect, global warming, and more. If you're interested in alternative videos, check out our videos on electromagnetic radiation. Thanks for watching!